Welcome to our full course on Intro to Quantum Mechanics, a journey through one of the most fascinating and pivotal areas of physics. This course is designed to unravel the complexities of quantum mechanics, making it accessible to anyone with an interest in understanding the fundamental principles that govern the microscopic world. Over the next 4 hours, we will embark on a comprehensive exploration, starting from the historical breakthroughs that paved the way for quantum theory, to the cutting-edge applications that define our technological landscape today. Our course is structured to gradually build your understanding, beginning with the birth of quantum theory. We will explore how Planck's solution to the blackbody radiation problem and Einstein's explanation of the photoelectric effect challenged classical physics and led to the development of quantum mechanics. As we delve into wave-particle duality, the uncertainty principle, and Schrödinger's equation, you will gain a deeper insight into the behavior of particles at the quantum level. Moving forward, we will apply these foundational principles to understand quantum states, superposition, entanglement, and the intriguing implications of quantum measurement. This course also covers the practical side of quantum mechanics, including its role in developing technologies such as lasers, semiconductors, and quantum computers. Through engaging explanations and visual illustrations, we aim to make the abstract and counterintuitive concepts of quantum mechanics as clear and intuitive as possible. So, whether you're a student, a curious learner, or just someone fascinated by the mysteries of the universe, this course will provide you with a solid understanding of quantum mechanics. We'll explore both its theoretical underpinnings and its real-world applications, preparing you to appreciate the quantum world that underlies our classical reality. Let's embark on this quantum journey together, exploring the fundamental laws that are as profound as they are transformative. Quantum mechanics, a fundamental theory in physics, describes nature at the smallest scales of energy levels of atoms and subatomic particles. It emerged in the early 20th century as scientists began to discover that classical physics could not explain the behavior of the atomic and subatomic world. The story of quantum mechanics is a tale of how human curiosity and ingenuity unraveled the mysteries of the universe on an unimaginably small scale. The journey into quantum mechanics began with Max Planck's groundbreaking work in 1900, when he proposed that energy is quantized to solve the blackbody radiation problem. This was a radical departure from classical physics, which treated energy as a continuous flow. Albert Einstein built on Planck's ideas in 1905, introducing the concept of the photon in his explanation of the photoelectric effect, further challenging classical notions by suggesting that light behaves both as a particle and a wave. The development of quantum mechanics accelerated in the 1920s with the contributions of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, among others. Bohr introduced his model of the hydrogen atom, which incorporated quantized energy levels. Heisenberg formulated the uncertainty principle, revealing the intrinsic limitations in measuring certain pairs of physical properties simultaneously. Schrödinger developed wave mechanics, providing a mathematical framework that described the wave-like behavior of particles. Together, these discoveries laid the foundation for a new understanding of the physical world, profoundly altering our comprehension of nature's laws. Quantum mechanics has since become the backbone of modern physics, explaining phenomena that classical physics cannot and leading to numerous technological innovations, from semiconductors and lasers to MRI machines and quantum computers. It challenges our classical intuitions about the world, inviting us to embrace a reality where particles can exist in multiple states simultaneously and where the act of observation can fundamentally alter the outcome of events. The history of quantum mechanics is not just a chronicle of scientific progress, it's a testament to the human quest for knowledge, pushing the boundaries of what we know about the universe. Quantum mechanics is not just a cornerstone of modern physics, it's the foundation upon which much of today's technology is built. Its principles and discoveries have opened up new pathways in science and engineering, leading to innovations that have transformed our world. From the screens on our smartphones to the computers that power the internet, quantum mechanics plays a crucial role in the development and functioning of numerous technologies that are central to our daily lives. In the realm of computing, quantum mechanics has paved the way for the development of quantum computers. These devices leverage the principles of superposition and entanglement to perform complex calculations at speeds unimaginable with classical computers. While still in the early stages of development, quantum computing promises to revolutionize fields such as cryptography, drug discovery, and artificial intelligence, offering solutions to problems that are currently beyond our reach. The impact of quantum mechanics extends beyond the digital world. It's at the heart of medical imaging techniques like MRI, enabling doctors to see inside the human body with unprecedented clarity. In the field of materials science, quantum mechanics has led to the discovery of new materials with extraordinary properties, from superconductors that transmit electricity without loss to quantum dots, used in displays for their vibrant colors and energy efficiency. Quantum mechanics also plays a vital role in understanding and harnessing the energy of the sun through solar panels, improving their efficiency and making renewable energy more accessible. It's clear that quantum mechanics is not just a theoretical framework for physicists. It's a driving force behind technological advancements that shape our society and economy. As we continue to explore the quantum world, we can expect to uncover even more ways in which these strange and beautiful laws of nature can be harnessed to improve our lives and expand our understanding of the universe. The birth of quantum theory marks one of the most significant revolutions in the history of physics, fundamentally altering our understanding of the universe. It began in the early 20th century, amidst growing evidence that classical physics could not explain phenomena at the atomic and subatomic levels. The classical view held that energy was continuous, but experiments suggested otherwise, leading to a paradigm shift that would redefine physics. Max Planck's work in 1900 provided the first cornerstone of quantum theory. Faced with the black-body radiation problem, Planck proposed that energy is not exchanged continuously, but in discrete amounts or quanta. This hypothesis, initially seen as a mathematical trick, laid the groundwork for a new way of thinking about the interaction between matter and energy. Planck's constant, a fundamental quantity that arises from his work, is now central to quantum mechanics, symbolizing the quantum of action that underpins the theory. Albert Einstein further advanced quantum theory in 1905 by explaining the photoelectric effect, the phenomenon where light shining on certain materials can eject electrons from the surface. Einstein proposed that light itself is quantized, consisting of particles called photons. This radical idea, for which he won the Nobel Prize, demonstrated the dual nature of light, behaving as both a wave and a particle, and cemented the concept of quantization in physics. The birth of quantum theory challenged the deterministic nature of classical physics, introducing a world where probabilities and uncertainties reign. It opened the door to understanding the behavior of atoms and subatomic particles, leading to the development of quantum mechanics as a comprehensive framework for describing the quantum world. This shift not only deepened our understanding of the universe, but also paved the way for technological advancements that have transformed society, from the electronics that power our devices to the medical technologies that save lives. The inception of quantum theory is a testament to the power of human curiosity and the endless pursuit of knowledge, marking the beginning of a new era in physics. The story of quantum theory begins with an attempt to understand a phenomenon known as blackbody radiation, a problem that perplexed physicists at the turn of the 20th century. A blackbody is an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence. Classical physics predicted that such a body would emit radiation in all frequencies, but it failed to accurately predict the intensity of the radiation at different wavelengths, leading to the so-called ultraviolet catastrophe, where classical theories predicted an infinite amount of energy being radiated at high frequencies, a clearly nonsensical result. Enter Max Planck, a German physicist who in 1900 proposed a radical hypothesis to solve this conundrum. Planck suggested that energy is not emitted or absorbed in a continuous flow, as was previously thought, but rather in discrete packets, which he called quanta. According to Planck's hypothesis, the energy of these quanta is directly proportional to the frequency of the electromagnetic radiation, with the constant of proportionality, now known as Planck's constant. This hypothesis was revolutionary because it contradicted the classical view of energy as a continuous variable, introducing the idea that energy exchange could only occur in discrete amounts. Planck's quantum hypothesis was the key to accurately predicting the spectral distribution of blackbody radiation, perfectly matching experimental observations. This success marked the birth of quantum theory, fundamentally changing our understanding of energy and matter. Planck's work laid the groundwork for the development of quantum mechanics, a theory that would come to dominate physics in the 20th century. His hypothesis opened the door to a new way of thinking about the interactions between light and matter, leading to profound implications not just in physics, but across all areas of science and technology. The exploration of the quantum world further unraveled its mysteries with the study of the photoelectric effect, a phenomenon that classical physics could not adequately explain. When light is shone on certain materials, it causes the emission of electrons from the material's surface. According to classical wave theory, the energy of the emitted electrons should increase with the intensity of the light. However, experiments showed that the energy of the emitted electrons was instead dependent on the frequency of the light, and there was a certain threshold frequency below which no electrons were emitted, regardless of the light's intensity. Albert Einstein offered a groundbreaking explanation for the photoelectric effect in 1905, proposing that light itself is quantized, consisting of discrete packets of energy called photons. Each photon carries a quantum of energy proportional to its frequency, as described by Planck's constant. When a photon hits the surface of a material, it can transfer its energy to an electron. If this energy exceeds the work function of the material, the minimum energy needed to remove an electron from the surface, the electron is ejected. This explanation not only solved the puzzle of the photoelectric effect, but also provided compelling evidence for the particle-like behavior of light, challenging the classical wave theory of light. Einstein's work on the photoelectric effect was revolutionary, cementing the concept of photons and laying the foundation for the development of quantum mechanics. It showed that light could be understood as both waves and particles, a duality that would become a central theme in quantum theory. The photoelectric effect has since become a fundamental principle used in various technologies, including photovoltaic cells, which convert sunlight into electricity, and photoelectron spectroscopy, a technique used to study the electronic structures of materials. The insights gained from studying the photoelectric effect have had far-reaching implications, influencing not just the development of quantum theory, but also opening new avenues for technological innovation. Einstein's explanation of the photoelectric effect underscored the quantum nature of light and matter, heralding a new era in physics where the boundaries between particles and waves, energy and matter, began to blur. Niels Bohr, building on the foundation laid by Planck and Einstein, made significant strides in our understanding of atomic structure with his model of the hydrogen atom, introduced in 1913. Bohr proposed that electrons orbit the nucleus in discrete orbits without radiating energy, in contrast to the predictions of classical physics. This was a revolutionary concept, suggesting that only certain orbits are allowed, and each of these orbits corresponds to a specific energy level. Bohr's model was based on two key postulates. First, electrons in an atom move in circular orbits around the nucleus under the influence of electrostatic forces, but they do so without emitting radiation, contrary to what classical electromagnetism would predict. Second, an electron can jump from one allowed orbit to another, absorbing or emitting a photon in the process. The energy of this photon is equal to the difference in energy between the two orbits. This idea explained the discrete spectral lines observed in the light emitted by atoms, a phenomenon that had puzzled scientists for decades. The introduction of Bohr's model was a pivotal moment in the development of quantum mechanics. It provided a quantum explanation for the stability of atoms and the emission of light in discrete spectra, phenomena that could not be explained by classical theories. Bohr's work laid the groundwork for the quantum mechanical model of the atom, incorporating the wave-like behavior of electrons and leading to the development of the Schrödinger equation, which offers a comprehensive description of how electrons behave. Bohr's model of the hydrogen atom marked a significant step forward in our understanding of the microscopic world, blending the quantized nature of energy with the structure of atoms. It was a bold leap towards the quantum mechanical view of the atom that dominates modern physics, illustrating the intricate dance of particles and waves at the heart of quantum theory. Bohr's insights into atomic structure opened new pathways for the exploration of quantum phenomena, shaping the future of science and technology. Wave-particle duality is a fundamental concept in quantum mechanics that reveals the dual nature of matter and light. This principle posits that every quantum entity, such as photons, particles of light, and electrons, particles of matter, exhibits both particle-like and wave-like characteristics. The concept challenges classical intuition, which distinguishes clearly between waves and particles, and has profound implications for our understanding of the fundamental nature of reality. The roots of wave-particle duality trace back to the early 20th century, with significant contributions from scientists like Albert Einstein and Louis de Broglie. Einstein's explanation of the photoelectric effect provided the first evidence of the particle-like behavior of light, traditionally considered a wave phenomenon. Conversely, de Broglie introduced a groundbreaking hypothesis that matter, like electrons, could exhibit wave-like properties, characterized by the de Broglie wavelength. This was later confirmed by experiments such as the Davisson-Germer experiment, which demonstrated the diffraction of electrons, a behavior characteristic of waves. Wave-particle duality necessitates a new framework for understanding the behavior of quantum entities, one that differs markedly from classical physics. According to this principle, the nature of quantum entities during observation depends on the type of measurement performed. For example, light can behave as a wave, showing interference patterns in a double-slit experiment, or as a particle, transferring quantized energy to electrons in the photoelectric effect. Similarly, electrons can produce diffraction patterns when passed through a double slit, yet exhibit discrete impacts on a detector screen, highlighting their particle aspect. The concept of wave-particle duality has led to the development of the quantum field theory, where particles are understood as excitations in quantum fields that pervade the universe. This duality is not just a theoretical curiosity, but has practical implications in technologies such as electron microscopy, which relies on the wave nature of electrons to achieve high-resolution imaging. Wave-particle duality embodies the essence of quantum mechanics, illustrating the complex and often counterintuitive nature of the quantum world, where classical concepts of waves and particles merge into a unified quantum reality. De Broglie's hypothesis, proposed by the French physicist Louis de Broglie in 1924, marks a cornerstone in the development of quantum mechanics, introducing the revolutionary idea that matter possesses wave-like properties. De Broglie suggested that not only does light, traditionally understood as a wave, exhibit particle-like characteristics, as evidenced by photons, but particles of matter like electrons also exhibit wave-like behavior. This hypothesis was a radical departure from classical physics, which treated waves and particles as entirely separate entities. De Broglie posited that the wavelength of a matter wave is inversely proportional to its momentum, a relationship now famously encapsulated by the equation L/P, where L is the wavelength, h is Planck's constant, and p is the momentum of the particle. This equation implied that all matter, not just light, has a dual wave-particle nature, fundamentally changing our understanding of the quantum world. The smaller the mass of the particle, the larger its de Broglie wavelength, making wave-like properties more significant at the atomic and subatomic levels. The experimental validation of de Broglie's hypothesis came with the Davisson-Germer experiment in 1927, which demonstrated the diffraction of electron beams, a behavior characteristic of waves when they were passed through a crystal. This experiment not only confirmed de Broglie's hypothesis, but also provided a new way of observing the microscopic world, leading to the development of electron microscopy, which relies on the wave nature of electrons to achieve high-resolution images of tiny structures. De Broglie's hypothesis of matter waves has profound implications, bridging the gap between the macroscopic world, governed by classical physics, and the quantum realm, where quantum mechanics reigns. It challenges our classical intuition and opens up a new understanding of matter and energy, emphasizing the interconnectedness of the universe. The concept of matter waves is integral to quantum mechanics, laying the groundwork for the theory's development and its myriad applications in science and technology. The Davisson-Germer experiment, conducted in the late 1920s by American physicists Clinton Davisson and Lester Germer, stands as a pivotal moment in the history of quantum mechanics. This groundbreaking experiment provided the first direct evidence of the wave-like properties of electrons, thus confirming Louis de Broglie's hypothesis of matter waves. Before this experiment, the concept that particles could exhibit wave-like behavior was a theoretical curiosity with little empirical support. The Davisson-Germer experiment changed that, offering tangible proof of the dual nature of matter and fundamentally altering our understanding of the quantum world. Davisson and Germer set out to study the surface of a nickel crystal by bombarding it with a beam of electrons and observing how these electrons scattered off the crystal. They expected results consistent with the predictions of classical mechanics. However, what they observed was strikingly different. Instead of scattering randomly, as one might expect if electrons were simply particles, the electrons displayed patterns of interference. These patterns closely resembled those produced by waves interacting with an obstacle, in this case, the crystal lattice of nickel. The observed interference pattern was a clear indication that electrons, when passing through the crystal, behave not just as particles, but also as waves. The significance of the Davisson-Germer experiment cannot be overstated. By demonstrating the wave-like behavior of electrons, it provided empirical validation for de Broglie's hypothesis, which until then had lacked direct experimental evidence. This experiment was crucial in establishing the wave-particle duality concept as a central pillar of quantum mechanics. It showed that wave-particle duality was not an abstract mathematical idea, but a real phenomenon observable in the laboratory. The Davisson-Germer experiment opened new avenues in physics, paving the way for the development of quantum mechanics as a coherent and predictive theory. It also had profound implications for the way scientists understood the nature of matter and energy, revealing a much more complex and fascinating quantum realm, where particles could exhibit properties of both particles and waves. This experiment is a testament to the unpredictability of scientific discovery, where a seemingly straightforward investigation into the properties of electrons revealed one of the fundamental principles of quantum mechanics. Heisenberg's uncertainty principle, introduced by Werner Heisenberg in 1927, is a fundamental concept in quantum mechanics that marks a profound departure from classical physics. It states that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. The more accurately we know the position of a particle, the less accurately we can know its momentum, and vice versa. This principle is not a limitation of our measurement techniques or technology, but a fundamental property of the universe, arising from the wave-particle duality of matter. The uncertainty principle challenges the classical idea that the world operates like a machine, with every part moving in a predictable path. Instead, it introduces a fundamental limit to our knowledge of the quantum world, implying that at a microscopic level, the universe does not adhere to deterministic laws as previously thought. This principle has profound implications for the way we understand the behavior of particles at the quantum level, fundamentally changing our conceptual framework for physics. This principle is quantitatively expressed by the inequality dx/dp h2, where dx is the uncertainty in position, dp is the uncertainty in momentum, and h is the reduced Planck's constant divided by 2p. This equation mathematically formalizes the concept of uncertainty, making it one of the cornerstone ideas of quantum mechanics. It shows that the act of measurement affects the particle being measured, leading to a fundamental limit to precision that can be achieved. Heisenberg's uncertainty principle has far-reaching consequences, not only for theoretical physics, but also for the philosophical implications of science. It underlines the idea that reality at the quantum level is inherently probabilistic, rather than deterministic, introducing a level of fundamental randomness into the fabric of the universe. This principle is crucial for the development and interpretation of quantum mechanics, influencing various aspects of science and technology, including the fields of quantum computing and quantum cryptography, where it plays a pivotal role in understanding and exploiting the quantum properties of particles. The concept of Heisenberg's uncertainty principle is at the heart of quantum mechanics, fundamentally altering our understanding of the physical universe. It posits that there are inherent limits to the precision with which certain pairs of physical properties, like position and momentum, can be simultaneously known. This principle signifies a radical departure from the deterministic worldview of classical mechanics, where it was assumed that with enough information one could predict the future state of a system with absolute certainty. In contrast, the uncertainty principle introduces a fundamental element of indeterminacy into quantum theory, suggesting that at the quantum level, the behavior of particles is governed by probabilities rather than certainties. The implications of the uncertainty principle are profound and far-reaching. It challenges the classical notion that objects have definite properties independent of observation. Instead, it suggests that the properties of particles are not fixed until they are observed, and even then, they cannot be known with unlimited precision. This concept has led to a new understanding of the nature of reality, one in which the act of measurement plays a crucial role. The principle not only limits what we can know about the quantum world, but also indicates that particles themselves do not possess precise values of certain properties until they are measured. Beyond its philosophical implications, the uncertainty principle has practical consequences in the realm of science and technology. It lays the foundation for the field of quantum mechanics, influencing the development of technologies such as semiconductor devices, lasers, and quantum computing. In these technologies, the properties and behaviors predicted by quantum mechanics and inherently linked to the uncertainty principle are exploited to create functionalities that would be impossible under the classical laws of physics. Moreover, the uncertainty principle has catalyzed a shift in scientific thinking, prompting questions about the limits of human knowledge and the nature of reality. It illustrates how deeply the observer is intertwined with the observed, underscoring the complexity and interconnectedness of the universe. This principle not only reshapes our understanding of the micro-world, but also challenges us to rethink our place within the macrocosm, offering a humbling view of the limits of human understanding and the mysteries that lie at the foundation of the cosmos. Thought experiments have played a crucial role in the development and understanding of quantum mechanics, offering insightful, often paradoxical perspectives on the theory's fundamental principles. These mental exercises explore the implications of quantum mechanics without the need for physical experiments, allowing scientists to probe the depths of the theory's most enigmatic aspects. Notable among these is the Schrödinger's cat paradox, which illustrates the concept of superposition, the idea that a system can exist in multiple states simultaneously until it is observed. Schrödinger's cat involves a hypothetical scenario where a cat is placed in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the Geiger counter triggers the hammer to release the poison, killing the cat. According to quantum mechanics, the atom is in a superposition of decayed and not decayed states. Therefore, by extension, the cat is considered to be simultaneously alive and dead until the box is opened and the system is observed. This thought experiment challenges our classical intuition about the definiteness of states and the nature of reality, illustrating the bizarre implications of superposition and measurement in quantum mechanics. Another influential thought experiment is the EPR paradox, named after Einstein, Podolsky, and Rosen, who proposed it to question the completeness of quantum mechanics. The paradox involves two particles that have interacted in such a way that their properties are entangled. According to quantum mechanics, measuring a property of one particle instantly determines the corresponding property of the other, regardless of the distance separating them. This instantaneous action at a distance seems to violate the principle of locality and suggests that quantum mechanics might be incomplete or that there might be hidden variables determining the outcome of measurements. These thought experiments highlight the counterintuitive and often puzzling nature of quantum mechanics, challenging our conventional notions of reality, causality, and locality. They have spurred intense debates and further research, pushing the boundaries of our understanding of the quantum world. Through such mental explorations, scientists continue to unravel the intricacies of quantum mechanics, shedding light on its implications for the nature of reality itself. Thought experiments serve not only as tools for theoretical investigation, but also as sources of inspiration for experimental research, guiding us toward deeper insights into the quantum universe. The Schrödinger equation, formulated by Austrian physicist Erwin Schrödinger in 1926, is a fundamental equation in quantum mechanics that describes how the quantum state of a physical system changes over time. It plays a central role in the theory, analogous to Newton's second law in classical mechanics. This equation is pivotal because it provides a way to calculate the wave function of a system, which in turn determines the probability of finding particles like electrons in a certain position. The beauty and power of the Schrödinger equation lie in its ability to apply to a wide range of quantum systems, from atoms to molecules, making it a cornerstone of quantum physics. The equation comes in two main forms: the time-dependent Schrödinger equation which accounts for changes in the quantum state over time, and the time-independent Schrödinger equation, which applies to systems in a steady state. At its core, the Schrödinger equation introduces the concept of the wave function, a complex mathematical function that encapsulates the probabilities of finding a system in various possible states. The absolute square of the wave function gives the probability density of finding particles at different locations in space. Understanding and solving the Schrödinger equation opens the door to predicting the behavior of quantum systems with astonishing accuracy. It has been instrumental in explaining and predicting phenomena such as electron orbitals in atoms, the behavior of molecules in chemical reactions, and the properties of solids in material science. The equation's ability to describe the quantum world has not only confirmed the strange, probabilistic nature of quantum mechanics, but also allowed for practical applications, including the development of new materials, pharmaceuticals, and technologies like semiconductors and lasers. The Schrödinger equation embodies the essence of quantum mechanics, marrying the concepts of waves and particles into a single framework. Its introduction marked a significant leap forward in our understanding of the microscopic world, providing a mathematical language to describe the wave-like behavior of particles. As the backbone of quantum mechanics, the Schrödinger equation remains a tool of immense power and elegance, enabling scientists to explore the depths of the quantum realm and its myriad implications for the universe. The derivation of the Schrödinger equation marked a pivotal moment in the history of physics, intertwining mathematical elegance with profound physical insight. Erwin Schrödinger, in his pursuit to understand the underlying principles of quantum mechanics, sought to describe the behavior of particles not as discrete points moving through space, but as waves. This wave-based approach was inspired by the wave-particle duality observed in light and matter, suggesting that particles like electrons could also be described by wave functions. Schrödinger's equation emerged from the need to mathematically characterize how these wave functions evolve over time and space. At its core, the Schrödinger equation encapsulates the energy of a quantum system, balancing the kinetic and potential energy to predict the probability distribution of a particle's position and momentum. The time-dependent equation, which describes how the quantum state of a system changes, incorporates both the particle's mass and its wave-like nature through Planck's constant. The time-independent form, used for systems in a stable state, focuses on the spatial distribution of the wave function and is crucial for understanding the structure of atoms and molecules. The physical interpretation of the Schrödinger equation introduces the concept of the wave function, a fundamental entity in quantum mechanics that describes the quantum state of a particle or system. The wave function, denoted by the Greek letter psi, is a complex function whose magnitude squared gives the probability density of finding the particle at a certain position. This probabilistic interpretation, proposed by Max Born, was a radical departure from classical physics, which describes the universe in definite, deterministic terms. In the quantum realm, the wave function embodies the probabilities and uncertainties inherent in measuring quantum systems. The Schrödinger equation and its wave function offer a window into the quantum world, where particles exhibit both wave-like and particle-like properties. It has provided a foundation for much of modern physics and chemistry, enabling the development of quantum mechanics as a robust theoretical framework. The equation's ability to predict the behavior of particles at the atomic and subatomic levels has not only deepened our understanding of the natural world, but also paved the way for technological innovations in computing, medicine, and materials science, illustrating the profound impact of theoretical physics on our everyday lives. The Schrödinger equation, a cornerstone of quantum mechanics, manifests in two principal forms, the time-independent and time-dependent equations. Each version plays a critical role in describing the behavior of quantum systems, offering insights into the dynamics and properties of particles at the quantum level. The time-dependent Schrödinger equation provides a comprehensive description of a quantum system's evolution over time. It is formulated to account for the changes in a particle's wave function, px xt, where x represents the position and t denotes time. This equation is crucial for understanding how quantum states evolve, making it indispensable for predicting the outcomes of dynamic quantum processes and interactions. The time-dependent equation's ability to describe the temporal evolution of quantum systems underpins much of quantum mechanics, offering a window into the transient phenomena of the quantum world. In contrast, the time-independent Schrödinger equation is concerned with quantum systems in a steady state, where the system's energy remains constant over time. This form of the equation is particularly useful for analyzing the properties of atoms and molecules, such as the energy levels of electrons in an atom or the vibrational modes of molecules. It simplifies to a spatial equation, post-x, emphasizing the probability distribution of particles' positions without the explicit consideration of time. This equation is foundational for much of quantum chemistry and solid-state physics, providing essential insights into the structure and behavior of matter. Both forms of the Schrödinger equation are indispensable tools in the arsenal of physicists and chemists, enabling the exploration of the quantum landscape. The time-dependent equation allows for the prediction and understanding of dynamic quantum systems, while the time-independent form offers a static snapshot, revealing the inherent properties and potential energy landscapes of quantum states. Together, they encapsulate the dual aspects of quantum systems, bridging the gap between the microscopic quantum realm and the macroscopic world observed in experiments. Through these equations, the enigmatic behavior of particles at the quantum level becomes accessible, paving the way for advancements in technology and our understanding of the universe. Among the foundational problems illustrating the principles of quantum mechanics, the particle in a box and quantum tunneling stand out for their simplicity and profound implications. These concepts not only serve as crucial teaching tools, but also highlight the counterintuitive nature of the quantum world. The particle-in-a-box model is a fundamental quantum mechanical system that demonstrates how particles behave when confined within an impenetrable barrier. In this scenario, unlike in classical mechanics, a particle such as an electron is not free to move anywhere but is restricted to a defined region of space, leading to quantized energy levels. This quantization is a direct consequence of the wave-like nature of particles described by the Schrödinger equation. The particle can only occupy certain states, with specific energy levels, demonstrating the discrete nature of quantum systems. This model is pivotal in understanding phenomena in quantum chemistry and physics, including the behavior of electrons in atoms and the properties of semiconductors. Quantum tunneling, on the other hand, showcases the ability of particles to pass through barriers that would be insurmountable according to classical physics. This phenomenon occurs because the wave function representing a particle extends beyond the potential barrier, allowing for a non-zero probability that the particle can be found on the other side of the barrier. Quantum tunneling has profound implications and applications, including in nuclear fusion, where it enables protons to overcome their electrostatic repulsion, and in modern electronics, as it is the principle behind the operation of tunnel diodes and the scanning tunneling microscope. Both the particle in a box and quantum tunneling illustrate the fundamental departure of quantum mechanics from classical physics, predictability, and determinism. These concepts not only enrich our understanding of the quantum world, but also underscore the practical implications of quantum mechanics in technology and scientific research. They exemplify how quantum mechanics reshapes our understanding of particles and energy, opening up new realms of possibility in both theoretical exploration and technological innovation. Quantum states and superposition are foundational concepts in quantum mechanics that delve into the intrinsic nature of particles at the quantum level. A quantum state defines the state of a system or particle, encapsulating all its properties such as position, momentum, and spin. These states are described by wave functions, mathematical expressions that provide the probabilities of finding a particle in various positions or states. The beauty of quantum mechanics lies in its ability to describe particles not as isolated entities with definite properties, but as existing in multiple states simultaneously until measured. Superposition, a principle that arises directly from the concept of quantum states, is the ability of a quantum system to be in multiple states at the same time. It is not merely a theoretical curiosity, but a fundamental aspect of quantum mechanics, demonstrated vividly in experiments such as the double-slit experiment with electrons. When not observed, an electron passes through both slits simultaneously, interfering with itself, a phenomenon that can only be explained if the electron exists in a superposition of passing through each slit. Superposition underscores the probabilistic nature of quantum mechanics, where certainty is replaced by probabilities until a measurement is made. This concept has profound implications for the field of quantum computing. In classical computing, a bit is in one of two states, 0 or 1. However, in quantum computing, a quantum bit or qubit can exist in a superposition of both 0 and 1 states simultaneously. This allows quantum computers to perform many calculations at once, potentially solving problems in seconds that would take classical computers millennia. Superposition, therefore, is not just a fascinating aspect of quantum theory, but a principle that could revolutionize technology, encryption, and our entire computational paradigm. Understanding quantum states and superposition challenges our classical intuitions about the nature of reality, suggesting a world where objects can exist in multiple places or states simultaneously until observed. It opens the door to a universe far more complex and intertwined than previously imagined, where the act of measurement itself shapes the reality we observe. These concepts are at the heart of quantum mechanics, illustrating the rich and mysterious landscape that scientists continue to explore in the quest to understand the fundamental principles of the universe. Quantum interference is a fundamental phenomenon in quantum mechanics, showcasing the wave-like properties of particles such as electrons and photons. It occurs when two or more wave functions overlap, leading to a situation where the probability amplitude, which dictates the likelihood of finding a particle in a certain location, can add or cancel out. This effect is most famously demonstrated in the double-slit experiment, where particles like electrons are fired at a barrier with two slits. Instead of forming two distinct clusters, as one might expect from classical particles, the electrons create an interference pattern similar to waves on a screen behind the slits. This pattern of alternating bright and dark bands indicates areas of constructive and destructive interference, respectively, and provides compelling evidence of the wave-particle duality inherent in quantum mechanics. The implications of quantum interference extend far beyond the confines of theoretical physics, impacting technology and our understanding of the universe. In the realm of quantum computing, for example, quantum interference is a principle that allows qubits, the basic units of quantum information, to perform complex calculations far more efficiently than their classical counterparts. By exploiting the superposition of quantum states, where qubits can exist in multiple states simultaneously, quantum computers use interference to amplify correct pathways to a solution while canceling out incorrect ones, thereby solving certain types of problems at speeds unattainable by classical computers. Moreover, quantum interference has profound implications for our understanding of the fundamental nature of reality. It challenges classical intuitions about the distinctiveness of states and the independence of particles, suggesting a much more interconnected and dynamic quantum realm. This interconnectedness, exemplified by phenomena such as entanglement, where particles remain connected across vast distances, underscores the non-locality inherent in quantum mechanics. Quantum interference thus serves as a window into the quantum world, revealing the complex interplay between the wave and particle aspects of matter. Its implications stretch from the microscopic realm, where it guides the behavior of atoms and subatomic particles, to the macroscopic, influencing the development of technologies that could revolutionize computing, encryption, and our understanding of quantum phenomena. Through the study of quantum interference, we gain insights into the fundamental principles that govern the universe, highlighting the intricate and often counterintuitive nature of quantum mechanics. Quantum measurement and the concept of wave function collapse are pivotal aspects of quantum mechanics, challenging our classical understanding of observation and measurement. In the quantum realm, particles exist in states of superposition, embodying multiple potential outcomes simultaneously. However, upon measurement, this superposition collapses to a single state, the outcome of which can only be described probabilistically. This phenomenon is at the heart of the quantum measurement problem, raising fundamental questions about the role of the observer in the behavior of quantum systems. The act of measuring a quantum system is not merely a passive observation, but an active process that fundamentally alters the state of the system. Before measurement, a particle's properties, such as its position and momentum, are not determined. They are described by a wave function that encodes all possible outcomes. Measurement forces the system to choose one of these outcomes, leading to the collapse of the wave function. This collapse is instantaneous and non-deterministic, meaning that the specific outcome cannot be predicted ahead of time. only the probabilities of different outcomes. This concept challenges the classical notion of a deterministic universe, where the properties of particles are definite, and measurement simply reveals these properties without altering the system. In contrast, quantum mechanics suggests a universe where probabilities reign until observation collapses the wave function to a singular reality. The implications of this are profound, influencing not just the philosophy of science but also the development of technologies that leverage the probabilistic nature of quantum states, such as quantum cryptography and quantum computing. Quantum measurement and collapse underline the peculiar interplay between knowledge and reality in the quantum world. They highlight the inherent limitations in our ability to predict the behavior of quantum systems and the fundamental role that observation plays in shaping the fabric of reality. These concepts continue to fuel debates and research in the foundations of quantum mechanics, driving forward our understanding of the universe at its most fundamental level. The measurement postulate of quantum mechanics and the concept of wave function collapse are fundamental to understanding how observation affects quantum systems. According to the measurement postulate, when we measure a quantum system, we do not observe a superposition of states but a single definite state. This act of measurement causes the wave function, which encodes all possible outcomes of the measurement, to collapse to a particular state that corresponds to the observed outcome. This phenomenon is at the heart of the quantum mechanical framework, illustrating the profound impact of observation on the behavior of quantum entities. The wave function, a mathematical description of the quantum state of a system, represents the probabilities of finding the system in various possible states upon measurement. Before measurement, a quantum system can exist in a superposition, embodying multiple states simultaneously. However, upon observation, this superposition collapses to a single state, with the wave function instantaneously reducing to a state that reflects the outcome of the measurement. This collapse is non-deterministic, meaning that it is fundamentally unpredictable which state will be observed. Only the probabilities of the various possible outcomes can be determined beforehand. This concept challenges classical notions of reality and determinism, suggesting that quantum systems do not possess definite properties prior to measurement. Instead, properties such as position and momentum are probabilistically defined, with definite values emerging only upon observation. The measurement postulate and wave function collapse raise profound questions about the role of the observer in quantum mechanics and the nature of reality at the quantum level, leading to various interpretations of quantum mechanics aimed at explaining these phenomena. The implications of wave function collapse extend beyond theoretical physics, influencing the development of quantum technologies and our understanding of the universe. It underscores the intricacy of quantum mechanics, where the act of measurement plays a crucial role in defining the state of quantum systems and challenges us to rethink our concepts of reality and the universe's fundamental nature. Quantum entanglement and non-locality are among the most intriguing and counterintuitive aspects of quantum mechanics, challenging our classical notions of space and causality. Quantum entanglement occurs when pairs or groups of particles interact in ways such that the state of each particle cannot be described independently of the state of the others, even when the particles are separated by large distances. This means that a measurement performed on one entangled particle instantaneously affects the state of the other, regardless of the distance separating them, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. Non-locality, a principle closely associated with entanglement, refers to the apparent instantaneity of the correlation between entangled particles, challenging the classical view that influences can only propagate through space at the speed of light or slower. This instantaneous correlation does not imply that information is transmitted faster than light, which would violate relativity, but rather that entangled particles share a state that is not confined to any single location in space. The implications of quantum entanglement and non-locality are profound, both philosophically and practically. They suggest that at a fundamental level, the universe is deeply interconnected, with particles that can remain correlated across vast distances, hinting at a level of unity beneath the apparent separateness of the physical world. This has led to groundbreaking applications in quantum information science, including quantum computing, quantum cryptography, and quantum teleportation, where entanglement is harnessed to perform tasks that are impossible within the framework of classical physics. Quantum entanglement and non-locality continue to be subjects of intense research and debate, as scientists and philosophers grapple with their implications for our understanding of reality. These phenomena underscore the departure of quantum mechanics from classical intuitions, offering a glimpse into the enigmatic and interconnected nature of the quantum world, where the traditional concepts of space and time are challenged, and new possibilities for technology and understanding the universe emerge. The EPR paradox and Bell's theorem are pivotal concepts in quantum mechanics that delve into the peculiarities of quantum entanglement and challenge our understanding of the nature of reality. The EPR paradox, named after its proponents Einstein, Podolsky, and Rosen, was introduced in 1935 as a thought experiment designed to question the completeness of quantum mechanics. It revolves around the idea of entangled particles, which are so intimately connected that the state of one, no matter the distance separating them, instantly determines the state of the other. Einstein and his colleagues used this scenario to argue that quantum mechanics must be incomplete, proposing that there must be hidden variables determining the outcomes of measurements, which quantum mechanics does not account for. This paradox highlights the concept of spooky action at a distance, challenging the notion of locality, the idea that objects are only influenced by their immediate surroundings. Einstein found the non-local implications of quantum mechanics troubling, as they conflicted with the theory of relativity, which posits that no information can travel faster than the speed of light. The EPR paradox set the stage for decades of debate over the foundations of quantum mechanics, questioning whether it provides a full description of reality. Enter Bell's theorem, formulated by physicist John S. Bell in 1964, which provided a way to test the assertions of the EPR paradox. Bell's theorem offers a set of inequalities that must be satisfied if local hidden variables are responsible for quantum correlations, as suggested by EPR. Experiments testing Bell's inequalities have consistently violated them, supporting the predictions of quantum mechanics and the existence of entanglement. These results imply that particles can indeed be entangled in such a way that measuring one instantly affects the state of the other, regardless of the distance between them, affirming the non-local character of quantum mechanics. The EPR paradox and Bell's theorem have profound implications for our understanding of the universe, highlighting the fundamental role of entanglement in quantum mechanics and challenging classical intuitions about separability and the speed of information transfer. They underscore the non-local interconnectedness of the quantum world, where the act of measurement on one part of a system can instantaneously influence another, no matter how far apart they are. This has not only deepened our understanding of the quantum realm, but also paved the way for advancements in quantum technologies, such as quantum computing and quantum cryptography, exploring the practical applications of these intriguing quantum phenomena. Quantum mechanics and information theory intersect in a fascinating and complex manner, fundamentally altering our understanding of information processing and transmission in the quantum realm. This intersection has led to the development of quantum information science, a field that explores the implications of quantum mechanics for the storage, manipulation, and communication of information. Unlike classical information, which is binary and represented by bits, zeros and ones, quantum information is encoded in quantum bits or qubits, which can exist in a state of superposition, embodying multiple states simultaneously. The principles of quantum mechanics, such as superposition and entanglement, enable qubits to perform tasks that are beyond the reach of classical bits. For example, a pair of entangled qubits, even when separated by vast distances, remain connected in such a way that the state of one, whether it is observed or not, instantly influences the state of the other. This non-local property of quantum entanglement opens up new possibilities for quantum communication protocols, such as quantum teleportation, where the state of a qubit can be transferred from one location to another without physical transportation of the qubit itself. Furthermore, the concept of quantum superposition allows qubits to perform multiple calculations at once, offering a dramatic increase in computational power for certain tasks. This has profound implications for the fields of cryptography, where quantum algorithms could potentially break many of the cryptographic systems currently in use, and for the development of quantum computers, which could solve problems deemed intractable for classical computers, such as simulating complex quantum systems, optimizing large systems, and more. The marriage of quantum mechanics and information theory not only heralds a new era of technology, but also challenges our fundamental notions of what information is and how it can be manipulated and transmitted. As we delve deeper into the quantum world, the potential for revolutionizing computing, secure communication, and our understanding of the quantum processes underlying the universe becomes increasingly apparent. Quantum mechanics and information represent a frontier of both immense challenge and promise, poised to redefine the landscape of technology and science. Quantum bits, or qubits, are the fundamental building blocks of quantum computing, representing a significant leap beyond the binary bits of classical computing. Unlike a classical bit, which can be in one of two states, 0 or 1, a qubit can exist in a state of superposition, where it is both 0 and 1 simultaneously. This characteristic allows qubits to perform complex calculations at speeds unattainable by classical computers, harnessing the principles of quantum mechanics to process information in fundamentally new ways. The power of quantum computing lies in its ability to exploit the quantum phenomena of superposition and entanglement. When qubits become entangled, the state of one qubit instantly influences the state of another, no matter the distance between them. This entanglement enables a level of parallelism that is impossible in classical computing. For example, while a classical computer with n bits can only be in one of two impossible states at any given time, a quantum computer with n qubits can be in all of those two states at once, thanks to superposition. Quantum computing has the potential to revolutionize fields that require the processing of vast amounts of data and the execution of complex algorithms. This includes cryptography, drug discovery, financial modeling, and solving complex optimization problems. Quantum algorithms, such as Shor's algorithm for factoring large numbers and Grover's algorithm for searching unsorted databases, demonstrate the potential for quantum computers to solve certain problems exponentially faster than their classical counterparts. The basics of quantum computing, centered around the manipulation and measurement of qubits, mark the beginning of a new era in information technology. While the field is still in its infancy, with many technical challenges to overcome, the theoretical underpinnings suggest a future where quantum computing could alter our technological landscape, offering capabilities far beyond what is possible with classical computing. As research and development continue to advance, the principles of quantum mechanics will increasingly become intertwined with the way we process, store, and interpret information, opening new frontiers in science and technology. Quantum cryptography represents a groundbreaking application of quantum mechanics to secure communication. It leverages the principles of quantum mechanics, such as the uncertainty principle and quantum entanglement, to create communication channels that are theoretically immune to eavesdropping. One of the most well-known protocols in quantum cryptography is quantum key distribution, QKD, where two parties share a secret key generated through the exchange of qubits. Any attempt by an eavesdropper to measure these qubits would inevitably alter their state, thus revealing the presence of the intrusion. This method ensures that the key can only be known to the intended recipients, offering a level of security that is fundamentally underpinned by the laws of physics rather than computational complexity. Quantum teleportation, another fascinating concept born from quantum mechanics, allows for the transfer of quantum states between particles at distant locations, without physical transmission of the particles themselves. This process relies on the phenomenon of quantum entanglement, where entangled particles remain connected in such a way that the state of one, no matter how far away, instantly correlates with the state of the other. Through quantum teleportation, the complete quantum state of a particle can be transferred to another particle, effectively teleporting the state across space. While it might sound like science fiction, quantum teleportation does not allow for the teleportation of matter or energy, but rather the teleportation of information encoded in quantum states. These developments in quantum cryptography and teleportation are not just theoretical curiosities, but have practical implications for the future of secure communication and information processing. Quantum cryptography has the potential to revolutionize data security, making communication channels impervious to hacking attempts by utilizing the fundamental properties of quantum mechanics. Similarly, quantum teleportation could play a crucial role in the development of quantum networks and quantum computing, enabling the creation of highly secure, interconnected quantum systems. Together, quantum cryptography and teleportation exemplify the remarkable potential of quantum mechanics to transform technology and communication. They underscore a future where information and security are enhanced by the principles of quantum physics, leading to advancements that could have been scarcely imagined in the era of classical physics. As research in these areas progresses, the practical realization of these quantum technologies continues to draw closer, promising a new era of secure and efficient information transfer. Quantum mechanics, a cornerstone of modern physics, has led to revolutionary applications that have fundamentally transformed technology and our understanding of the universe. Its principles underpin a wide array of technologies that are pivotal to both everyday life and advanced scientific research. From the micro scale, like the design of semiconductors and lasers, to the macro scale, such as understanding the cosmos, the impact of quantum mechanics is profound and far-reaching. In the realm of technology, quantum mechanics is the foundation upon which modern electronics and photonics are built. Semiconductors, the heart of all electronic devices, from smartphones to computers, operate on principles that are directly derived from quantum mechanics. The behavior of electrons in materials, crucial for the development of transistors and diodes, can only be accurately described using quantum theory. Similarly, the laser, a device that emits a highly focused beam of light, is another application of quantum mechanics. It works on the principle of stimulated emission, predicted by Einstein and foundational to quantum optics, leading to innovations in medicine, communications, and manufacturing. Beyond these well-established technologies, quantum mechanics is driving the development of next-generation technologies like quantum computing and quantum cryptography. Quantum computing promises to solve problems intractable for classical computers by leveraging superposition and entanglement, offering new possibilities in drug discovery, cryptography, and complex system simulation. Quantum cryptography, on the other hand, uses the principles of quantum mechanics to create secure communication channels that are theoretically invulnerable to eavesdropping, providing a new standard for security in digital communications. The applications of quantum mechanics extend beyond practical technologies to enhance our understanding of the universe. It plays a crucial role in the fields of cosmology and particle physics, helping scientists explore the fundamental forces of nature and the early moments of the universe. The predictive power of quantum mechanics has been confirmed through countless experiments, making it not only a framework for understanding the microscopic world, but also a tool for pushing the boundaries of human knowledge and technology. The ongoing exploration of quantum mechanics continues to unlock new potentials, promising to usher in further advancements and innovations that we can scarcely imagine today. The applications of quantum mechanics are vast and transformative, touching nearly every aspect of modern technology. Among its most significant contributions are the development and understanding of lasers, semiconductors, and superconductors, each of which has revolutionized various fields of science and industry. Lasers, which stand for light amplification by stimulated emission of radiation, operate on principles directly derived from quantum mechanics. The process of stimulated emission, predicted by Albert Einstein and foundational to laser operation, involves the emission of a photon induced by an incoming photon of identical energy, leading to a coherent beam of light with unique properties. This quantum mechanical phenomenon has led to the development of lasers used in countless applications, from medical surgeries and optical communications to manufacturing and entertainment. Semiconductors, materials whose electrical conductivity lies between that of conductors and insulators, are at the heart of all modern electronics. The quantum mechanical theory of the solid state explains how electrons move through these materials, allowing for the precise manipulation of their electrical properties. This understanding has enabled the miniaturization of electronic components and the development of transistors, diodes, and integrated circuits, which are fundamental to computers, smartphones, and all forms of digital technology. Superconductors, materials that conduct electricity with no resistance below a certain temperature, represent another application of quantum mechanics with profound implications. The phenomenon of superconductivity, explained by the BCS theory in quantum mechanical terms, has led to the creation of technologies such as magnetic resonance imaging, MRI, in medicine, maglev trains, and the possibility of lossless power transmission. Quantum mechanics, not only explains the behavior of superconductors but also guides researchers in developing new materials that operate at higher temperatures, moving closer to practical everyday applications. These examples, lasers, semiconductors, and superconductors, illustrate just a fraction of the ways in which quantum mechanics has been applied to create technologies that shape our modern world. From the devices we use daily to the cutting-edge tools of scientific research, the principles of quantum mechanics underlie some of the most significant technological advances of the past century, demonstrating the power of fundamental science to drive innovation and transform society. Magnetic resonance. Imaging, or MRI, is one of the most profound technological advancements made possible by the principles of quantum mechanics. This medical imaging technique utilizes the principles of nuclear magnetic resonance, a quantum mechanical phenomenon, to visualize detailed internal structures of the body. By aligning the spin of nuclei in a strong magnetic field and then perturbing this alignment with radio frequency pulses, MRI machines can detect the energy released as the nuclei return to their original states. The resulting signals are used to create highly detailed images of organs and tissues, providing invaluable insights for diagnosis and treatment planning without the use of ionizing radiation. Beyond MRI, quantum mechanics has paved the way for a host of other technological advancements. Quantum dots, for example, are tiny semiconductor particles only a few nanometers in size that have unique optical and electronic properties due to quantum mechanics. These properties make quantum dots incredibly useful in a range of applications, from medical imaging and quantum computing to solar cells and light-emitting diodes, LEDs. The ability to precisely control the size and shape of quantum dots allows for the tuning of their color and brightness, leading to more vibrant displays and more efficient solar panels. Another groundbreaking application is in the field of quantum sensing, which exploits quantum systems to measure physical quantities with unprecedented precision. Quantum sensors leverage the extreme sensitivity of quantum states to external disturbances, enabling the detection of tiny changes in magnetic fields, gravity, rotation, or time. This technology has potential applications in navigation, mineral exploration, and even in the early detection of conditions such as Alzheimer's disease by measuring minute changes in brain activity. These examples illustrate just a fraction of how quantum mechanics has become intertwined with technological progress, pushing the boundaries of what's possible in medicine, computing, and materials science. From providing doctors with tools like MRI to explore the human body in stunning detail, to enabling new technologies like quantum dots and quantum sensors, the applications of quantum mechanics continue to expand, shaping the future of technology and offering promise for new discoveries and innovations. Spin and quantum statistics are crucial concepts in quantum mechanics that play a fundamental role in understanding the behavior of particles at the quantum level. Spin is a quantum property of particles that gives them an intrinsic angular momentum, akin to how a planet spins on its axis. However, unlike classical spinning objects, quantum spin does not involve physical rotation. Instead, it is a purely quantum mechanical property characterized by specific quantized values. This intrinsic spin has profound implications for the behavior of particles, affecting how they interact with magnetic fields and with each other. Quantum statistics, which include Fermi-Dirac and Bose-Einstein statistics, describe how systems of identical particles behave and interact. These statistics are determined by the spin of the particles involved. Fermions. Particles with half-integer spin follow Fermi-Dirac statistics and obey the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state simultaneously. This principle explains the structure of the periodic table and the behavior of electrons in atoms, molecules, and solids. Bosons, on the other hand, have integer spin and follow Bose-Einstein statistics. Unlike fermions, bosons can occupy the same quantum state, leading to phenomena such as superfluidity and Bose-Einstein condensation. This collective behavior of bosons at low temperatures results in unique properties, such as the ability of superfluid helium to flow without viscosity. Spin and quantum statistics are not just abstract concepts. They have practical applications in technology and research. For example, the understanding of electron spin is fundamental to the field of spintronics, which aims to develop electronic devices that use spin in addition to charge. Quantum statistics are also crucial in the development of quantum computers, where the manipulation of quantum states of particles could revolutionize computing power and efficiency. These concepts underline the exotic and often counterintuitive behaviors observed in the quantum world, showcasing the richness and complexity of quantum mechanics. Electron spin and the Stern-Gerlach experiment are pivotal concepts and discoveries in quantum mechanics that have deepened our understanding of the quantum world. Spin is a fundamental quantum property of particles, representing their intrinsic angular momentum. Unlike classical angular momentum, which arises from particles rotating in space, spin is an inherent characteristic of quantum particles, including electrons, which gives them a magnetic moment. The concept of electron spin introduces a two-valued quantum number, which can be either up or down, and plays a crucial role in the quantum theory of magnetism and the structure of atoms. The Stern-Gerlach experiment, conducted in 1922 by Otto Stern and Walter Gerlach, was a groundbreaking experiment that provided the first direct evidence of the quantum property of spin. In the experiment, a beam of silver atoms was passed through a non-uniform magnetic field, resulting in the beam splitting into two distinct paths. This outcome was surprising because it demonstrated that the angular momentum of the atoms, and consequently their magnetic moments, were quantized. The results could only be explained by introducing the concept of quantum spin, showing that the atoms had only certain allowed orientations in the magnetic field, corresponding to the discrete values of spin. The discovery of electron spin and the insights gained from the Stern-Gerlach experiment have had profound implications for the field of quantum mechanics. They have led to a deeper understanding of the Pauli exclusion principle, which states that no two electrons in an atom can have the same set of quantum numbers, thereby explaining the arrangement of electrons in atoms and the periodic table of elements. Furthermore, the concept of spin is integral to the technology of magnetic resonance imaging, MRI, which uses the spin properties of nuclei to produce detailed images of the inside of the human body. Electron spin and the Stern-Gerlach experiment exemplify the counterintuitive and fascinating nature of quantum mechanics. They highlight the discrete, quantized nature of the universe at the microscopic level, challenging classical intuitions and opening new avenues for technological innovation and scientific discovery. The concept of spin has become a cornerstone of quantum physics, with implications and applications that span from the fundamental structure of matter to cutting-edge technologies in computing and medicine. Fermions and bosons are the two fundamental classes of particles in the universe, distinguished by their intrinsic spin and governed by different quantum statistics. Fermions, which include particles such as electrons, protons, and neutrons, have half-integer spins like 1, 2, 3, 2, and so on. One of the key characteristics of fermions is their adherence to the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. This principle states that no two fermions can occupy the same quantum state within a quantum system simultaneously. It is the Pauli exclusion principle that underlies the unique arrangement of electrons in atoms, explaining the structure of the periodic table and the chemical properties of elements. Bosons, on the other hand, have integer spins such as 0, 1, 2, and so forth. This category includes particles like photons and the Higgs boson. Unlike fermions, bosons can occupy the same quantum state, allowing them to bunch together. This ability is the basis for phenomena such as superconductivity and superfluidity, where particles move en masse without friction. Bosons are often force carriers in the universe, mediating the fundamental forces of nature such as the electromagnetic force carried by photons and the weak force carried by W and Z bosons. The distinction between fermions and bosons and the Pauli exclusion principle have profound implications for the behavior of matter and energy at the quantum level. The exclusion principle explains why matter occupies space and why atoms do not collapse under the forces that draw their electrons and nuclei together. It is also crucial for the stability and complexity of the universe, determining the structure of atoms and molecules and, consequently, the variety of chemical reactions that fuel life in the cosmos. Understanding fermions, bosons, and the Pauli exclusion principle offers deep insights into the fundamental nature of the universe. These concepts are not merely abstract notions, but have practical applications in technologies such as lasers, semiconductors, and quantum computers, showcasing the remarkable ways in which quantum mechanics manifests in the natural world and drives technological innovation. Many-body quantum systems represent a complex and fascinating frontier in quantum mechanics, encompassing systems with a large number of interacting particles. These systems are crucial for understanding a wide range of physical phenomena, from the behavior of solids and liquids to the dynamics of quantum fluids and the intricacies of quantum information processing. The complexity of many-body systems arises from the interaction between particles, which can lead to emergent phenomena that are not evident when considering individual particles in isolation. One of the fundamental challenges in studying many-body quantum systems is the exponential growth of the system's Hilbert space, with the addition of each particle, making exact solutions practically unattainable for large systems. This complexity necessitates the development of sophisticated theoretical models and computational techniques to approximate the behavior of these systems. Techniques such as mean field theory, density functional theory, and the use of quantum Monte Carlo simulations have been instrumental in advancing our understanding of many-body systems. The study of many-body quantum systems has led to the discovery of remarkable quantum states of matter, such as Bose-Einstein condensates and quantum Hall fluids. These states exhibit unique properties, such as superfluidity and quantized conductance, which have profound implications for our understanding of quantum phase transitions and the role of symmetry in quantum physics. Moreover, many-body systems are at the heart of quantum computing and information theory, where entanglement between multiple particles can be harnessed to perform computations and secure communications beyond the capabilities of classical systems. Exploring the complexities of many-body quantum systems continues to push the boundaries of our understanding of the quantum world, challenging theoretical and computational limits. As research progresses, it promises not only deeper insights into the fundamental principles of physics, but also the development of new technologies and materials with novel properties, inspired by the intricate dance of particles governed by the laws of quantum mechanics. The introduction to the quantum mechanics of multi-particle systems marks a significant expansion of our exploration into the quantum world, venturing beyond the behavior of individual particles to understand the complex interactions and phenomena that arise when multiple particles are considered together. Multi-particle systems are fundamental to a vast array of physical phenomena, from the solidity of matter to the intricacies of chemical reactions, and they require a more sophisticated theoretical framework to describe their behavior accurately. In classical mechanics, the behavior of systems with many particles can often be understood by considering the sum of individual particle interactions. However, in the quantum realm, the principles of superposition and entanglement introduce profound complexities. Quantum mechanics teaches us that particles in a multi-particle system cannot always be treated as independent entities. Instead, their states are often correlated, meaning the state of one particle can be inherently tied to the state of another, regardless of the distance separating them. This non-local connection, a hallmark of quantum entanglement, defies classical intuition and is a key feature that distinguishes multi-particle quantum systems from their classical counterparts. The formalism for dealing with multi-particle systems in quantum mechanics often involves the construction of wave functions, or quantum states, that encompass all the particles in the system. This approach must also account for the indistinguishability of particles of the same type, leading to the symmetrization principle for bosons, particles that follow Bose-Einstein statistics, and the anti-symmetrization principle for fermions, particles that follow Fermi-Dirac statistics. These principles have profound implications for the physical behavior of the system, influencing everything from the structure of atoms and molecules to the properties of solids and the universe at large. Understanding the quantum mechanics of multi-particle systems opens the door to explaining and predicting a wide range of physical phenomena, from the peculiarities of quantum statistics that give rise to phenomena like superconductivity and superfluidity, to the foundational aspects of quantum field theory. As we delve deeper into the quantum behavior of multi-particle systems, we unlock new insights into the fabric of the universe, revealing the exquisite order and complexity that emerges from the quantum laws governing the microscopic world. Quantum entanglement in complex systems represents one of the most intriguing and foundational aspects of quantum mechanics. This phenomenon occurs when particles become so deeply connected that the state of one cannot be described independently of the state of the others, even when the particles are separated by large distances. Entanglement challenges our classical notions of locality and causality, showing that quantum systems can exhibit correlations that defy classical explanation. In complex systems, entanglement plays a crucial role in understanding the collective behavior of particles. It is not merely a curiosity observed in isolated pairs of particles. Rather, it is a pervasive feature of the quantum world, underlying the properties of solids, the behavior of quantum fluids, and the workings of quantum computers. Entanglement in complex systems can lead to phenomena such as quantum superposition of states on a macroscopic scale, evident in the coherence of laser beams and the frictionless flow of superfluids. The study of quantum entanglement in complex systems also has profound implications for quantum information science. It forms the basis of quantum computing, where entangled states are used to perform operations on multiple qubits simultaneously, vastly increasing the power of quantum computers compared to classical ones. Furthermore, entanglement is central to quantum cryptography, which exploits the sensitivity of entangled states to eavesdropping, thereby ensuring secure communication. Entanglement's role in complex systems highlights the interconnectedness of the quantum world, where the whole cannot be simply inferred from the sum of its parts. As researchers continue to probe the depths of quantum entanglement, they not only unravel the mysteries of the quantum universe but also pave the way for new technologies that leverage these quantum correlations, pushing the boundaries of what is technologically possible and deepening our understanding of the universe's fundamental nature. Quantum field theory, QFT, is a fundamental framework in physics that extends quantum mechanics to systems with an infinite number of degrees of freedom, such as fields, and integrates it with the principles of special relativity. QFT is essential for describing the behavior of elementary particles and the forces through which they interact. It provides the theoretical underpinning for the standard model of particle physics, which explains how particles like quarks and electrons interact via forces mediated by particles such as photons and gluons. At the heart of QFT is the concept that particles can be created and destroyed, and are excitations of underlying fields that permeate the universe. For example, photons are excitations of the electromagnetic field, while electrons are excitations of an electron field. This perspective allows QFT to describe not just the properties of particles, but also their interactions and the creation of particle-antiparticle pairs from the vacuum, showcasing the dynamic nature of the quantum world. QFT also introduces the concept of virtual particles, which are transient fluctuations that mediate forces between particles. These virtual particles, though not directly observable, have real effects on the interactions between particles. For example, the force between two electrons is understood in QFT as being mediated by the exchange of virtual photons. This framework has been incredibly successful in providing accurate predictions for a wide range of phenomena, from the outcomes of high-energy particle collisions to the detailed structure of atoms. Quantum field theory represents a profound synthesis of the concepts of quantum mechanics and special relativity, offering a comprehensive framework for understanding the fundamental forces of nature. It challenges our classical notions of space and time, particles and waves, and has led to groundbreaking discoveries, including the prediction and subsequent discovery of particles like the Higgs boson. As the foundation of modern particle physics, QFT continues to push the boundaries of our knowledge, driving the search for a more complete theory of the universe. Quantum field theory, QFT, represents a cornerstone of modern physics, blending the principles of quantum mechanics with those of special relativity to provide a comprehensive framework for understanding the fundamental forces and particles that make up the universe. It is the language in which the standard model of particle physics is formulated, explaining the interactions between elementary particles through the exchange of force-carrying particles. QFT's importance lies in its ability to describe phenomena across a vast range of scales, from the behavior of quarks and leptons to the dynamics of cosmic rays. At its core, QFT treats particles as excitations of underlying fields that extend throughout space and time. This approach allows for the creation and annihilation of particles, a feature not accommodated by classical physics or non-relativistic quantum mechanics. One of the most striking implications of QFT is the prediction of virtual particles, transient entities that mediate forces between particles. These virtual particles, although not directly observable, play a crucial role in explaining the interactions that govern the behavior of matter at the most fundamental level. QFT has led to numerous groundbreaking predictions and discoveries, including the existence of quarks, the Higgs boson, and the unification of electromagnetic and weak forces. Its predictive power and experimental verification, particularly in the realm of quantum electrodynamics, QED, have made it one of the most successful theories in the history of physics. QED, a subset of QFT, describes how light and matter interact and has been tested to an extraordinary degree of accuracy. The significance of QFT extends beyond particle physics, influencing cosmology, condensed matter physics, and the ongoing quest for a theory of quantum gravity. As a fundamental theory, QFT provides the framework within which nearly all of the physical sciences operate, underscoring its importance in our quest to understand the universe. It remains an active area of research, with physicists continually exploring its implications, pushing the boundaries of our knowledge, and seeking a deeper, more unified understanding of the fundamental forces of nature. The concept of virtual particles and force mediation is one of the most intriguing and fundamental aspects of quantum field theory, QFT. Virtual particles are not particles in the traditional sense. They cannot be directly observed and do not exist independently in the same way that real particles do. Instead, they are transient fluctuations within quantum fields, arising and disappearing in fleeting moments. Despite their ephemeral nature, virtual particles play a crucial role in mediating forces between real particles, allowing them to interact over distances. In QFT, forces between particles are understood as the exchange of virtual particles. For instance, the electromagnetic force between two charged particles, such as electrons, is mediated by the exchange of virtual photons, the quanta of the electromagnetic field. This exchange can be thought of as one particle emitting a virtual photon, which is then absorbed by the other particle, transferring momentum and energy in the process. This mechanism underlies not only the electromagnetic force, but also the weak and strong nuclear forces, each mediated by their respective virtual particles, such as W and Z bosons for the weak force, and gluons for the strong force. Virtual particles are also responsible for some of the subtle effects in quantum physics, such as the Casimir effect, where virtual photons between two closed parallel plates in a vacuum exert a measurable force. Furthermore, the presence of virtual particles contributes to the vacuum energy, leading to phenomena like the Lamb shift in the energy levels of hydrogen atoms. These effects, predicted by QFT, have been experimentally verified, underscoring the theory's accuracy and the reality of virtual particles' effects, despite their intangibility. The concept of force mediation by virtual particles not only provides a unified framework for understanding the fundamental interactions in the universe, but also challenges our classical notions of empty space and force transmission. It reveals a dynamic, fluctuating vacuum teeming with activity, fundamentally altering our understanding of the vacuum and the nature of forces. Through the lens of QFT, the universe is seen as a vibrant tapestry woven from quantum fields and their excitations, with virtual particles playing a pivotal role in the fabric of reality. Quantum electrodynamics, QED, and quantum chromodynamics, QCD, are two of the most important theories within the framework of quantum field theory, QFT, each describing one of the fundamental forces of nature. QED is the first and most successful quantum field theory, formulated to explain and predict electromagnetic interactions between charged particles through the exchange of photons. It is a cornerstone of the standard model of particle physics, providing a comprehensive description of the interactions between light, photons, and matter, charged particles such as electrons and quarks. QED's predictions have been tested to an extraordinary degree of precision, making it one of the most accurate theories in the history of physics. Quantum chromodynamics, on the other hand, is the theory that describes the strong force, the fundamental force responsible for holding the nuclei of atoms together. Unlike electromagnetic force, which acts between charged particles, the strong force acts between quarks, the building blocks of protons and neutrons. QCD introduces the concept of color charge, analogous to electric charge in electromagnetism, and posits that the strong force is mediated by particles called gluons. Gluons, unlike photons in QED, carry color charge themselves, leading to the unique property of the strong force known as confinement. Quarks are never found in isolation but are always bound together in composite particles known as hadrons, which include protons and neutrons. The interplay between QED and QCD in the Standard Model is a beautiful demonstration of the unification of forces within the quantum framework. While QED deals with the force that operates over long distances and governs the structure of atoms and molecules, QCD describes the force that acts over very short ranges, binding quarks together within the confines of a nucleon. Despite their differences, both theories share the common language of QFT and have significantly deepened our understanding of the universe at the most fundamental level. Together, QED and QCD exemplify the power of quantum field theories to describe the forces of nature in a unified manner. Their development has not only expanded our understanding of the quantum world, but also led to numerous technological advancements and experimental discoveries. From the precision measurements of atomic spectra to the exploration of the quark-gluon plasma, the insights provided by QED and QCD continue to push the boundaries of our knowledge, challenging us to uncover the deeper principles that govern the universe. Quantum electrodynamics, QED, is the quantum field theory of the electromagnetic force, describing how light and matter interact through the exchange of photons, the fundamental particles of light. QED is a pillar of modern physics, providing a framework that combines the principles of quantum mechanics with the theory of special relativity to explain electromagnetic phenomena at the quantum level. It accounts for a wide range of phenomena, including the scattering of light, the structure of atoms, and the creation of particle-antiparticle pairs. At the heart of QED lies the concept that charged particles, such as electrons, interact by emitting and absorbing photons, which carry the electromagnetic force between them. This process is governed by the rules of quantum mechanics, which dictate the probabilities of various interactions. Unlike classical electromagnetism, where forces are described by continuous fields, QED treats the electromagnetic force as discrete exchanges of photons. These exchanges can happen even in a vacuum, leading to fluctuations in the electromagnetic field that influence the properties of particles and the vacuum itself. QED has been extraordinarily successful in predicting and explaining the outcomes of experiments with remarkable precision. For instance, it provides corrections to the energy levels of electrons in hydrogen atoms, the Lamb shift, and precisely predicts the magnetic moment of the electron, agreeing with experimental measurements to many decimal places. These successes have made QED one of the most tested and confirmed theories in physics. The basics of QED not only deepen our understanding of the interaction between light and matter, but also have practical applications in technologies such as lasers, LEDs, and quantum computing. By detailing how photons mediate the electromagnetic force, QED enables the development of technologies that manipulate light at the quantum level, paving the way for advancements in communication, imaging, and information processing. QED remains a vibrant field of research, continually refining our understanding of the universe and driving technological innovation. Quantum electrodynamics, QED, is the quantum field theory of the electromagnetic force, providing a comprehensive framework for understanding the interactions between light, photons, and matter, particularly charged particles such as electrons and positrons. QED stands as one of the most precise and successful theories ever developed, allowing for incredibly accurate predictions of phenomena ranging from the scattering of light by atoms to the energy levels of electrons in hydrogen. At the heart of QED lies the principle that light and matter interact through the emission and absorption of photons. These interactions are governed by the exchange of virtual photons, quantum particles that mediate the electromagnetic force between charged particles. This exchange can manifest in various phenomena, such as the attraction or repulsion between electrons, the emission of light by an excited atom, or the deflection of light by a charged particle. QED also explains the fine structure of atomic spectra, slight deviations in the energy levels of electrons that cannot be accounted for by classical electromagnetism or earlier quantum models. Through the concept of virtual particles and the interactions they mediate, QED provides corrections to these energy levels, predictions that have been confirmed to extraordinary precision through experimental measurements. Furthermore, QED describes how the vacuum itself is not empty, but filled with virtual particles and antiparticles that constantly appear and disappear, contributing to phenomena such as the Lamb shift, where these virtual particles shift the energy levels of atomic orbitals. The development and success of QED mark a significant achievement in the quest to unify the description of all forces under a single theoretical framework. Its ability to accurately predict and describe the interaction of light and matter not only underscores the power of quantum field theory, but also continues to influence a wide range of applications in physics, chemistry, and material science, reflecting the fundamental nature of electromagnetic interactions in shaping the physical world. Quantum chromodynamics, QCD, is the branch of quantum field theory, QFT, that describes the strong force, one of the four fundamental forces of nature, which binds quarks together to form protons, neutrons, and other hadrons. Central to QCD is the concept of color charge, an intrinsic property of quarks and gluons that is analogous to electric charge in electromagnetism, but with three types: red, green, and blue. The interplay of these color charges, mediated by gluons, the carriers of the strong force, ensures the stability and confinement of quarks within hadrons, preventing them from being isolated in free states. Gluons are unique among force carriers because they themselves carry color charge, allowing them to interact with each other. This property leads to the phenomenon of asymptotic freedom, where quarks behave as if they are almost free of each other at extremely high energies or close proximity, a feature that has been experimentally confirmed in high-energy particle collisions. Conversely, at lower energies or larger distances, the force between quarks becomes so strong that it confines them within hadrons, a behavior that prevents the observation of free quarks. The theoretical framework of QCD successfully explains the complex spectrum of hadrons observed in particle physics experiments and provides a comprehensive understanding of the strong interactions that govern nuclear matter. It also predicts the existence of exotic states of matter, such as quark-gluon plasma, a state of matter thought to have existed just after the Big Bang, where quarks and gluons are not confined within hadrons but exist in a free state. This plasma has been created and studied in heavy ion collision experiments, providing a glimpse into the conditions of the early universe. Introduction to QCD opens a window into the fundamental structure of matter, revealing the intricate dynamics of quarks and gluons that underpin the existence of the visible universe. As research in QCD continues to evolve, it not only deepens our understanding of the strong force and the fabric of the quantum world, but also challenges and inspires advancements in theoretical physics, particle physics experiments, and our quest for a unified theory of all fundamental forces. Quantum mechanics and cosmology intertwine at the most fundamental levels, exploring the universe from the smallest particles to the vastness of cosmic structures. This fascinating intersection sheds light on the origins and evolution of the universe, as well as the fundamental forces and particles that govern it. Quantum mechanics, with its principles of uncertainty, superposition, and entanglement, provides a crucial framework for understanding the early universe, particularly during the first moments after the Big Bang, where the conditions were governed by quantum phenomena. One of the most profound connections between quantum mechanics and cosmology is the concept of quantum fluctuations. In the incredibly high-energy environment of the early universe, these fluctuations could have been amplified to macroscopic scales by the rapid expansion of space-time known as inflation. This process is believed to have seeded the initial density variations that, through gravitational attraction, led to the formation of galaxies, stars, and ultimately the large-scale structure of the universe we observe today. Thus, quantum mechanics plays a crucial role in explaining not just the behavior of particles, but also the distribution and evolution of matter across the cosmos. Additionally, quantum mechanics has implications for understanding the nature of black holes and the universe's ultimate fate. The interplay between quantum mechanics and general relativity, particularly in extreme conditions such as those found near black holes, poses intriguing questions about information loss, the fabric of space-time, and the connection between quantum processes and gravitational phenomena. These questions are at the heart of ongoing research in theoretical physics, driving efforts to unify quantum mechanics with general relativity into a coherent theory of quantum gravity. The integration of quantum mechanics and cosmology continues to push the boundaries of our understanding, suggesting a universe where the quantum and cosmic are inextricably linked. From the tiniest quantum fluctuations to the vast expanse of the universe, the principles of quantum mechanics offer insights into the cosmos's birth and evolution, highlighting the fundamental unity of the physical world. As research progresses, the dialogue between quantum mechanics and cosmology promises to uncover deeper truths about the universe and our place within it, bridging the gap between the quantum and the cosmic in our quest to understand the ultimate nature of reality. Quantum fluctuations in the early universe play a pivotal role in our understanding of cosmology and the formation of the cosmic structures we observe today. In the realm of quantum mechanics, fluctuations are temporary changes in energy at a point in space, arising from the uncertainty principle. These fluctuations are an inherent feature of the quantum vacuum, leading to the brief appearance of particle-antiparticle pairs that pop into and out of existence. In the context of the early universe, particularly during the inflationary period, these quantum fluctuations were dramatically expanded from the microscopic to the macroscopic scale, laying the groundwork for the large-scale structure of the universe. The inflationary model proposes that the universe underwent an exponential expansion in its first fractions of a second, magnifying the quantum fluctuations present in the early quantum field. As inflation stretched the fabric of space-time, it also stretched these fluctuations, freezing them in as variations in the density of the universe. These variations in density became the seeds for the formation of galaxies, stars, and other cosmic structures, as regions of slightly higher density gravitationally attracted more matter, growing over billions of years into the complex structures we observe in the universe today. This process illustrates a direct link between the laws of quantum mechanics and the large-scale structure of the cosmos, showing how initial quantum fluctuations can lead to the birth of stars and galaxies. The cosmic microwave background radiation, a relic of the early universe, provides empirical evidence for this theory. Minute variations in this radiation map directly back to the quantum fluctuations of the inflationary epoch, offering a snapshot of the universe at its infancy and supporting the theory that quantum processes played a crucial role in shaping the cosmos. Quantum fluctuations in the early universe highlight the profound connection between quantum mechanics and cosmology, bridging the gap between the smallest scales of existence and the vast expanses of the cosmos. These fluctuations underscore the universe's quantum origins and provide a foundational mechanism for the emergence of structure and complexity from the uniformity of the Big Bang, emphasizing the intrinsic unity between quantum phenomena and cosmic evolution. Quantum mechanics and black holes represent one of the most fascinating intersections in modern physics, blending the principles of quantum theory with the extreme gravitational phenomena predicted by general relativity. Black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape, pose intriguing questions when examined through the lens of quantum mechanics. The study of black holes has unveiled phenomena such as Hawking radiation, a theoretical prediction that suggests black holes are not entirely black, but emit radiation due to quantum effects near their event horizons. The concept of Hawking radiation arises from the application of quantum field theory in curved space-time, suggesting that particle-antiparticle pairs spontaneously form near the event horizon of a black hole. Typically, these pairs annihilate each other almost immediately, but if one particle falls into the black hole while the other escapes, the black hole loses mass, leading to its gradual evaporation over time. This process, while incredibly slow for stellar mass black holes, introduces a fundamental connection between quantum mechanics, thermodynamics, and gravity, suggesting that black holes can thermodynamically behave like black bodies, emitting radiation with a temperature inversely proportional to their mass. Furthermore, quantum mechanics raises profound questions about the information content of objects that fall into black holes. According to quantum theory, information cannot be destroyed, but the apparent consumption of all matter and energy by a black hole suggests otherwise. This paradox has led to significant debate and research, driving forward our understanding of quantum gravity and the need for a unified theory that seamlessly integrates quantum mechanics with general relativity. The exploration of black holes through the lens of quantum mechanics continues to challenge our understanding of the universe, pushing the boundaries of known physics. It highlights the need for a deeper theoretical framework that can fully describe the quantum aspects of gravity and spacetime, a pursuit that remains one of the most compelling quests in theoretical physics. As we delve further into the quantum mechanics of black holes, we inch closer to uncovering the mysteries of the universe, from the smallest particles to the vast unseen phenomena that shape the cosmos. Hawking radiation and the information paradox are among the most intriguing aspects of the interplay between quantum mechanics and general relativity, particularly in the context of black holes. Hawking radiation, a theoretical prediction made by physicist Stephen Hawking in 1974, suggests that black holes are not completely black, but emit radiation due to quantum effects near their event horizons. This radiation results from the creation of particle-antiparticle pairs in the vacuum near the event horizon. If one particle falls into the black hole while its partner escapes, the black hole loses a tiny amount of its mass, emitting what we now call Hawking radiation. This phenomenon introduces the possibility that a black hole could eventually evaporate completely, given enough time. However, this leads to the information paradox, a fundamental puzzle in theoretical physics. According to quantum mechanics, information, the physical state of all particles, cannot be destroyed. But if a black hole evaporates completely through Hawking radiation, what happens to the information about the particles that had fallen into it? This question challenges the principle of quantum mechanics, that information must be conserved, suggesting a conflict between quantum theory and general relativity, which posits that anything that crosses the event horizon is lost to the outside universe. The information paradox has spurred numerous theories and debates among physicists. Some propose that information is somehow encoded in the Hawking radiation, allowing it to be preserved, albeit in a highly non-trivial way that we do not yet understand. Others suggest that the information might be stored in a remnant left over after the black hole evaporates, or that it could be lost in a way that requires a modification of our understanding of quantum mechanics. This paradox sits at the heart of the quest for a theory of quantum gravity that can reconcile the laws of quantum mechanics with those of general relativity. The exploration of Hawking radiation and the information paradox not only deepens our understanding of black holes, but also pushes the boundaries of modern physics, challenging us to rethink the fundamental principles that govern the universe. As research progresses, resolving the information paradox may lead to groundbreaking insights into the nature of reality, space-time, and the fabric of the cosmos, marking a pivotal step toward unifying the theories of the very large and the very small. The concept of entanglement and the Firewall paradox are at the forefront of discussions about the intersection of quantum mechanics and general relativity, particularly in the context of black holes. Quantum entanglement, a phenomenon where particles become interconnected in such a way that the state of one, no matter how distant, instantly influences the state of the other, challenges our classical understanding of information transfer and locality. This peculiar quantum behavior becomes even more intriguing when considered alongside black holes, giving rise to what is known as the black hole firewall paradox. The firewall paradox arises from a conflict between the principles of quantum mechanics and the predictions of general relativity about the nature of black hole event horizons. According to classical general relativity, an event horizon is unremarkable, allowing matter to pass through smoothly. However, quantum mechanics, with its insistence on the conservation of information, suggests a different story. If quantum information must be preserved, as posited by the principles of quantum mechanics, then the information about particles falling into a black hole must somehow be encoded in the Hawking radiation it emits. This leads to a paradox. For the information to be conserved, there must be a mechanism at the event horizon, a firewall of high-energy particles, that would disrupt the smooth passage into the black hole, contradicting the predictions of general relativity. This paradox highlights a deep and unresolved tension between the two pillars of modern physics. On the one hand, the concept of entanglement suggests that information is never lost, not even when swallowed by a black hole. On the other hand, the existence of a firewall seems necessary to preserve this information, but at the cost of altering our understanding of space-time near a black hole. The firewall paradox challenges physicists to rethink the fundamental principles underlying the universe, pushing the boundaries of our theoretical frameworks. The ongoing debate and research into entanglement, Hawking radiation, and the firewall paradox underscore the complexities and mysteries at the heart of theoretical physics. These discussions not only deepen our understanding of black holes, but also drive the quest for a unified theory of quantum gravity that can reconcile the seemingly incompatible realms of quantum mechanics and general relativity. As such, the exploration of these paradoxes is not just an academic endeavor, but a journey to the very edges of human knowledge, where the answers to some of the universe's greatest mysteries lie waiting to be discovered. The measurement problem and the various interpretations of quantum mechanics delve into the heart of what quantum mechanics tells us about reality. The measurement problem arises from the quantum mechanical postulate that the act of measurement causes the wave function, a mathematical representation of the quantum state of a system, to collapse from a superposition of states into a single state. This raises profound questions about the nature of reality in the absence of observation. If a quantum system exists in all possible states simultaneously until measured, what does this say about the existence of a definite reality prior to measurement? This problem has led to the development of multiple interpretations of quantum mechanics, each attempting to provide a coherent philosophical framework for understanding the nature of quantum reality. The Copenhagen interpretation, one of the oldest and most widely taught, posits that the wave function collapse upon measurement is fundamental, and that quantum mechanics does not prescribe a reality independent of observations. In contrast, the many worlds interpretation suggests that all possible outcomes of quantum measurements actually occur, with each outcome realized in a separate branching universe, thus avoiding the need for wave function collapse. Another interpretation, the de Broglie-Bohm theory or pilot wave theory, reintroduces determinism into quantum mechanics by suggesting that particles have definite positions and velocities at all times, guided by a pilot wave that determines the probabilistic outcomes we observe. Meanwhile, the transactional interpretation proposes that wave function collapse results from a handshake between waves moving forward and backward in time, a concept that offers a novel way to think about quantum interactions. The diversity of these interpretations underscores the philosophical challenges posed by quantum mechanics. While all interpretations make the same empirical predictions and thus cannot be distinguished by experiments, they offer different perspectives on the nature of reality, the role of the observer, and the fundamental structure of the universe. The measurement problem and its interpretations continue to fuel debates among physicists and philosophers, highlighting the rich interplay between physics and philosophy in our quest to understand the quantum world. The measurement problem in quantum mechanics is a fundamental issue that challenges our understanding of the nature of reality and the role of observation in the physical world. It arises from the quantum mechanical postulate that the act of measurement causes a quantum system to collapse from a superposition of states, where it simultaneously exists in multiple states, to a single, definite state. This phenomenon raises perplexing questions. If quantum systems do not possess definite properties until measured, what does that imply about the state of reality when it's not being observed? Does this mean that physical reality is somehow dependent on the presence of an observer? The significance of the measurement problem extends beyond theoretical physics, touching on deep philosophical inquiries about the nature of existence and knowledge. It challenges the classical view that the universe exists in a determinate state, independent of our observation, suggesting instead that reality is intrinsically probabilistic and fundamentally interconnected with the act of measurement. This has profound implications for our understanding of the universe, suggesting a more dynamic and complex relationship between observers and the physical world than previously thought. Furthermore, the measurement problem highlights the limits of classical logic when applied to the quantum realm, and prompts the exploration of alternative interpretations of quantum mechanics, each with its own philosophical implications. For instance, does the wave function represent physical reality or merely our knowledge of it? Are there parallel universes for every possible outcome, as posited by the many worlds interpretation? Or does reality emerge from the interactions of particles across time, as suggested by the transactional interpretation? The ongoing debate and investigation into the measurement problem underscore the foundational role of quantum mechanics in shaping our understanding of the physical universe. It continues to spur both scientific and philosophical discussions, driving advancements in quantum theory and technology, and challenging us to reconsider our assumptions about reality, causality, and the nature of existence itself. The measurement problem remains a crucial puzzle in our quest to unravel the mysteries of the quantum world, reflecting the intricate and fascinating interplay between the observed and the observer. The diverse interpretations of quantum mechanics offer various philosophical perspectives on the theory's foundational aspects, particularly regarding the nature of reality, the behavior of particles at the quantum level, and the role of the observer. Among these interpretations, the Copenhagen interpretation and the many worlds interpretation stand out for their distinctive approaches and implications. The Copenhagen interpretation, developed in the 1920s by Niels Bohr and Werner Heisenberg, posits that quantum mechanics does not provide a description of an objective reality, but rather deals with probabilities of observing various outcomes. According to this view, a quantum system exists in all possible states until it is measured, at which point the wave function collapses to a single outcome. This interpretation emphasizes the role of measurement and the practical aspects of quantum mechanics, sidestepping questions about the reality of the wave function prior to observation. In contrast, the many worlds interpretation proposed by Hugh Everett in the 1950s takes a radically different approach. It suggests that all possible outcomes of quantum measurements actually occur, each in its own separate parallel universe. According to this interpretation, the universe constantly splits into multiple histories or branches, where every possible outcome of every event defines its own history or world. This eliminates the need for wave function collapse, offering a deterministic universe, but at the cost of introducing an infinite number of parallel universes. Other notable interpretations include the de Broglie-Bohm theory, which introduces hidden variables to maintain particle determinism and trajectories, and the transactional interpretation, which views quantum interactions as transactions that involve standing waves moving backward and forward in time. Each interpretation attempts to address the peculiarities of quantum mechanics, from the dual nature of particles and waves to the entanglement and superposition of states, offering different perspectives on the underlying reality these phenomena suggest. The diversity of interpretations reflects the profound challenges quantum mechanics poses to our classical notions of reality and causality. While these interpretations differ in their philosophical underpinnings and implications for the nature of reality, they all conform to the empirical predictions of quantum mechanics. The debate over which interpretation, if any, correctly describes the nature of the quantum world continues to inspire both scientific investigation and philosophical inquiry, highlighting the richly interconnected nature of physics and philosophy. As we reach the conclusion of our exploration into the world of quantum mechanics, let's revisit some of the key concepts that have illuminated our understanding of the universe at its most fundamental level. Quantum mechanics, a pillar of modern physics, challenges our classical views of reality with its counterintuitive principles and phenomena, such as wave-particle duality, superposition, and entanglement. These principles reveal that particles like electrons and photons can exhibit both wave-like and particle-like properties, depending on the nature of observation. The concept of superposition, where quantum systems can exist in multiple states simultaneously until measured, introduces a probabilistic nature to the quantum world. This leads to the phenomenon of quantum entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of another, regardless of the distance separating them. These phenomena underscore the non-locality and interconnectedness of quantum systems, challenging our notions of space and causality. Furthermore, the measurement problem and the various interpretations of quantum mechanics, from the Copenhagen interpretation to the many worlds interpretation, highlight the deep philosophical questions that quantum mechanics poses about the nature of reality and the role of the observer. Each interpretation offers a different perspective on how to reconcile the theory's mathematical formalism with our observations of the physical world. Quantum mechanics has not only deepened our understanding of the universe's fabric, but also paved the way for numerous technological advancements, from semiconductors and lasers to quantum computing and encryption. As we continue to explore and unravel the mysteries of the quantum realm, the principles of quantum mechanics will undoubtedly play a central role in shaping the future of science and technology, challenging us to reimagine the possibilities of what can be understood, measured, and achieved. The future of quantum mechanics research promises to be as transformative and profound as its inception over a century ago. As we delve deeper into the quantum realm, we stand on the brink of new discoveries that could further revolutionize our understanding of the universe and spur technological advancements across multiple fields. The ongoing exploration of quantum entanglement, quantum computing, and the quest for a unified theory of quantum gravity are just a few areas where significant breakthroughs are anticipated. Quantum entanglement, with its intriguing implications for information transfer and the fundamental nature of reality, remains a rich field of study. Research into entanglement could lead to unprecedented advancements in quantum communication and encryption, providing secure communication channels immune to eavesdropping. Furthermore, the strange properties of entangled particles continue to challenge our notions of space and time, potentially leading to deeper insights into the fabric of the universe. Quantum computing, powered by the principles of superposition and entanglement, is poised to redefine the landscape of computation, data processing, and cryptography. With the capability to solve problems that are currently intractable for classical computers, quantum computing could revolutionize fields ranging from materials science to pharmaceuticals, optimizing complex systems and speeding up the discovery of new drugs. The race to build a scalable, fault-tolerant quantum computer is on, promising a future where quantum computing's full potential can be harnessed. On the theoretical front, one of the most tantalizing goals of modern physics is to develop a quantum theory of gravity that can seamlessly integrate quantum mechanics with general relativity. Such a theory would not only unify the fundamental forces of nature, but also provide a coherent description of the earliest moments of the universe and the enigmatic interiors of black holes. This pursuit could fundamentally alter our understanding of the cosmos, revealing new dimensions of reality and possibly even new forms of matter and energy. As we venture further into the quantum domain, the future of quantum mechanics research holds the promise of unveiling the universe's deepest secrets. It challenges us to rethink our understanding of reality, pushing the boundaries of what is possible in science, technology, and our conceptual grasp of the universe. The journey ahead is filled with unknowns, but one thing is certain: the quantum revolution is far from over, and its continued exploration will undoubtedly continue to reshape our world. As we conclude our journey through the fascinating world of quantum mechanics, it's clear that we've only scratched the surface of understanding the underlying principles that govern the universe at the smallest scales. The exploration of quantum mechanics is not just an academic endeavor. It's a journey into the heart of reality itself, challenging our perceptions and expanding our understanding of the cosmos. The theories and experiments we've discussed illuminate the complexity and beauty of the quantum world, a realm full of mysteries still to be unraveled. The future of quantum mechanics promises to be as intriguing and revolutionary as its past. With advancements in technology and theoretical research, we stand on the brink of new discoveries that could further transform our understanding of the universe and lead to practical applications beyond our current imagination. From quantum computing and teleportation to the unification of the forces of nature, the potential for breakthroughs is boundless. Your curiosity and passion for learning can contribute to these advancements, propelling us forward into the unknown. To deepen your understanding of quantum mechanics and stay abreast of the latest developments, I encourage you to explore a variety of resources. Books such as Quantum Mechanics, The Theoretical Minimum by Leonard Susskind and Art Friedman, and The Elegant Universe by Brian Greene offer accessible introductions to complex topics. Online courses from platforms like Coursera and edX, along with lectures available on YouTube from leading universities, provide further avenues for exploration. Engaging with these materials can enhance your knowledge and spark your curiosity. In closing, let this journey into quantum mechanics be just the beginning of your exploration. The field is vast and the questions are deep, inviting all who are curious to ponder the nature of reality. Whether you're a student, a researcher, or simply someone fascinated by the wonders of the universe, your contributions and insights are valuable. Keep asking questions, seeking answers, and exploring the boundless frontiers of quantum mechanics. The path to understanding the cosmos is a shared journey, and every step forward enriches us all. Continue to explore, learn, and marvel at the mysteries of the quantum world.